Right, section 2 is going to be all about similar polygons. We're going to start off by going over some terminology first. We're going to review an old term, congruent polygons. Remember, this is polygons with congruent matching angle measures and side lengths. So all the same angles, all the same sides. It looks like the same shape twice. It's the exact same figure. Similar polygons is a little bit different. Now, I want you to underline the fact that it is similar, not congruent. Similar and congruent are different. Similar polygons are polygons with congruent matching angle measures, but not the side lengths. So they're the exact same angles, not the exact same sides. The matching side lengths do make equal ratios, though. So in a sense, you can think of these as same shape, but different sizes. The last piece, or the last term we're going to look at, is scale factor. It's a number that multiplies quantities evenly. For polygons, this multiplies the side lengths. So for example, we'd say this door is twice the height and width of that door. So it would be, if you were to measure the height of one door and got 5 feet, the other door would be 10 feet. That would also scale its width. So if the first door was 3 feet wide, the second door would be 6 feet wide. So the scale factor is 2 in that case. So let's look at an example here of identifying each group of figures, or the polygons, as similar or not similar. Now remember, similar means they have matching angle measures, but not the side lengths. So it's like they're the exact same shape, but different sizes. Group A here, they're all quadrilaterals, so they all have 4 sides. If we look at them, though, these 3 looks like they all have right angles. On the bottom 3, though, none of those angles appear to be right angles. So we can see already, although they are all quadrilaterals, they don't all have matching or the same angle measures. So we'd say that that group is not similar. They're not congruent angles. Let's look at group B here. In this case, it looks like we have, again, all quadrilaterals, and they're all a certain kind of quadrilateral. They all appear to be squares. Remember, squares would all have right angles in each of these corners, and the ratio of their sides would all be the same. So let's say on this little one here, this side length was 1, and this side length was 3. Well, if this was 1 and this is 3, this is 1, this is 3. 1 to 3 is the same as 1 to 3. We'll change it and do like 5 and 5 on this one. 1 to 5 is the same as 1 to 5. And then 3 to 5 is the same as 3 to 5. So these are all the same exact shape, but just different sizes. So yes, these ones would be similar. Same shape, different size. That's what we mean by similar polygons. Same thing with this group here. Again, they're not all necessarily pointed in the same direction, but we have similar polygons here because they are the same exact shape. They're just different sizes. Example 2, we have 2 different triangles, ABC and JKL. They have this little squiggly line in between them, and it's just one squiggly line. I want to come over here and go over some notation real quick. I can make that a little bit bigger. When it's the one squiggly line over the equal sign, that's when they are congruent. Remember, congruent means they are exactly equal in all things. If it's just the one squiggly line, that means they are similar. So this notation right here is saying if triangle ABC is similar to triangle JKL. They're not congruent triangles, they are similar. What's asked of us is that we need to write the congruent statements for the angles and write proportions for the sides. Well, just like if we had these 2 triangles being congruent, this statement means that they all match up. So we can say angle A is congruent to angle J, because these were both the first ones. A, J. The next piece we could say then, angle B is congruent to angle K. B and K. And we could say lastly then that angle C is congruent to angle L. C and L. So they all matched up. So again, all of the angles have to be the exact same. That would make the exact same shape, but they're going to be different sizes. So this is what the proportions would look like. This side, I'm going from first to last, A to C, is the same as first to last, J to L. So that's our first ratio. The ratio of AC to JL is found right there. Now if we do the first and the second of this triangle compared to the first and the second of this triangle, AB to JK. Remember, these two ratios are the exact same. A to C compared to J to L is going to be the same exact ratio as AB compared to JK. And then the last one then, B to C and K to L. Now that's what we would write out if we were just looking at a congruency statement. To make it easier to visualize this, I drew a little picture. This way we can see how A to C matches up with JL. That was this ratio here. Those ones are kind of our matching lengths. So let's say that A to C was 2 and J to L was 1. We'd have a ratio of 2 to 1. So all the other ratios here have to match that 2 to 1 piece, so that 2 to 1 ratio. The next one we have is A to B and J to K. So if A to B was 4, J to K would have to be 2, because it would match that 2 to 1 ratio. So we'd have 4 to 2, which could reduce down to 2 to 1. And lastly, BC, oops, is this blue one, compared to K to L. If B to C was 6, K to L would be 3. So we'd have 6 to 3, which again would reduce to 2 to 1. So you can see how all of these ratios, they're the same exact ratio even though they're written with different numbers, but they would all match up because ABC is exactly twice as big as JKL. Example 3, write a similarity statement for these two quadrilaterals. Similarity statements are going to be just like our congruency statements, only these figures are not congruent. They're not the exact same. Here we see a length of 5, here it's 2.5, so it's exactly half of it. Same thing, here's a length of 6, here it is a length of 3, it's exactly half. 7, exactly half of that is this 3.5. 4, exactly half is this 2. So these are the exact same shape, but different sizes. So when we write a similarity statement, again, like our congruency statement, we just match the pieces up. So A matches with E, then B, C, D. So we could start by saying A, B, C, D, this figure, is similar, not congruent. We'll use this one squiggle, this similar, to E, F, G, H. Now, let's say we didn't want to start with A and go A, B, C, D. What if we wanted to start at C and go the other direction? So we call this one C, B, A, D. Well, C matches with G, and we'd have to go around this one. So G, F, E, H. So we could also write the statement as C, B, A, D is similar to G, F, E, H. It really doesn't matter. There are multiple ones you could do. Again, like our congruency statements, the only rules are everything has to match up. So if you started with D on one, you'd have to start with H on the other. And you just have to make sure all of your letters match up in their corresponding spots. Example 4. Are these quadrilaterals similar? Why or why not? And when we look at some of our lengths, we have like 5 and 5. That's a ratio of 1 to 1. We have 3 to 3. That's also a ratio of 1 to 1. So the side lengths do make equivalent ratios. On here though, in this corner we have a right angle. In fact, we have right angles in all of our corners. In this figure we have 120 degrees and 60 degrees. So our angles do not match up. So in this case we would say these figures are not similar. They do not have matching equal angles. You can tell just by looking at them they are not the same shape, even though they are pretty much the same size. 5 and 5, 3 and 3. Because they are not the same shape though, they would not be considered similar. Example 4, part B, are these quadrilaterals similar? Why or why not? Now in this case, if we look at all of our angles, 90 degrees, 90, 90, 90, 90 degrees, 90, 90, 90. So they do all have the same angle measure. If we look at some of the sides, 3 to 3, that's a 1-to-1 ratio. 5 to 3, that is not a 1-to-1 ratio, that's a 5 to 3 ratio. So our side lengths do not make the same ratios. So even though they have all the same angles, it doesn't actually make the same looking shape. So this one, or in this case, we'd say they are not similar. Again, the side lengths do not make equal ratios, or another way of saying that or thinking about it, they do not make the same shape. So these ones would not be considered similar. Example 5, part A. Oops. Cover these up. Solve for the missing parts in these similar figures. If we are given that MNPQ, so this figure is similar to RSTU, we need to find X, Y, and Z. Now notice M matches with R, so this one and this one are supposed to be the same. N matches with S, this one and this one. So as you look at these shapes, this one is not only smaller, but it's kind of flipped around, or it's like somebody put a mirror right here and flipped it over that mirror. So it's kind of hard to see because it's not necessarily in the exact same spot. However, these are similar, so there is a ratio between all of their sides. So first thing we want to take apart and look at is we need to solve for X. X is going to be in the same spot as this 25. So we'd put X over 25 as one of our ratios. One of the sides that we do know on our smaller one is this 18, M to N, matches up with this 30. So 18 over 30 equals X over 25. So now we kind of have our proportion set up. To solve for any proportion, we cross multiply. 18 times 25 and 30 times x. We get the equation 30x equals 450. Divide both sides by 30, and we would get x equals 15. So our missing side x, we know is 15. Same thing, we need to find this side length y. Y matches up with 15 over here. Again, we also still know that 18 matches up with 30. We'll do the small ones on top, or the lengths of the smaller figure on top, lengths of the bigger figure on bottom when we make our proportion. 18 over 30 equals y over 15. Oops, these are actually backwards. Good thing we caught that. Again, you always need to match up. 30 and y are on the bigger one, so these should match up on bottom. I think that's going to change my equation now. Yep, I did that wrong. 18y, because 18 times y when we cross multiply. There we go, and there we go. 18y is going to come out to, change this, 450. Divide both sides by 18, so 450 divided by 18 is going to be, oops, come here, 25. So y in this case should not be 9, it should be 25. So this would be our work for those two. Z, this angle is going to match up because Z is in the spot where R is. R matches with M, so it's this angle. Angles, remember, are always going to be the exact same on similar figures, so it's going to be exactly 115. Example 5, part B. Solve for the missing parts in this figure. Given that we have quadrilateral A, B, C, D, and it is similar to A, M, N, P. We need to find B to M, so that's this length. We need to find B to C, that's this length. And P to D, that would be this length. So, if we're looking for this one, B to M, and we know that this piece is 30 and this is 45, well, this is 45, that means this one is 45. 45 minus 30 means that that one would be 15. At 15 feet or inches or centimeters, whatever it is, missing right here. To solve for BC, we don't have enough information just to subtract. We need to use the fact that these are similar to make a proportion. The proportion we would set up would put sides of the little one compared to sides of the bigger one. 30 matches with 45. 40 matches with our missing piece. 30 over 45 equals 40 over x. I'm going to call this length x. To solve, we cross multiply. 45 times 40 and 30 times x. So the equation we're left with then is 30x equals 1,800. Divide both sides by 30 and we get x equals 60. So this length here is going to be 60. If this length is 60 and this is 40, we can just subtract the two and get that PD equals 20. We'll do example 5 on last video then.